I want to go after the first example. Now remember, I give you a copy of these examples in the lecture notes tab. You can download them in Word or PDF. And all I did here is that I just clipped part A of this thing here. So what I want to do here is that I want to, so on this thing here, what it's saying here is that I want to do what? I want to draw a motion diagram for each of the motions. There's parts A, B, and C. I want to use dots, velocity vectors, and I want to identify intervals. Intervals are the most important thing to identify, okay? You really want to pay attention to the intervals here. Okay, so let's go look at this thing here. So the first thing that I want to do here is that it says that I'm going to do A, so it says a speed skater moving across frictionless ice at 8 meters a second hits a 5-meter wide patch of rough ice. She slows steadily and then continues at 6 meters per second. Now, when I'm thinking time here, I'm not calculating time. I'm only trying to get a picture of the motion here. Okay, a picture of the motion. So I could imagine that there's a series of dots that are going. So the first thing that I see here is it says what? She's moving on frictionless ice for 8 meters a second. And then she's going to go to 6 meters a second, which is a slower speed. So the scaling is somewhat important, but not so crucial that you're like trying to calculate like, you know, how many squares and calculating partial squares. I don't think so. I wouldn't do that. So what I'm going to do here is that my scaling doesn't matter so much, but the image matters most. Okay, so here I go. So the first thing that I imagine here is that I have a series of points. So the ice skater is coming in. And what I'm seeing here is that she's coming in at constant velocity. And then at some point, there's the start of the rough ice. Now, how many seconds does it take for the rough ice? I don't care. That's not important. What is important is the overall picture. So let's draw it out. So the way I see it here is that I'm going to start here. Now note that she's already moving at constant velocity. So here I'm going to say constant velocity. And so that means I already know that she's moving at constant velocity. So when she gets to this point 0, I know that there's an interval beforehand that tells me that she was moving at constant velocity. So then I'm going to come in and I'm going to do this. And so here's my constant velocity. So here's my V's. And I know that these V's here, because they're in the first interval, I'm going to call them 1. So I know that V1 is 8 meters per second. And I'm going to say to the right. Question. She hits the rough ice. Is the speed at point 3 equal to, the same, or greater than the speed at 2 or 1? Right? So the question I'm asking, is it the same, smaller, larger? Is the speed, I'm asking about speed 3. Is the speed at 3 the same as smaller or larger at point 2?
Wouldn't it be smaller?
Okay. So if it's smaller, I have to look at the intervals, right? So let's look. So let's look at this interval. That interval gives me that V1 at V2, right? Now let's look at this interval right here. Is this interval the same between 2 and 1 as it is this 3 to 2?
Yes.
Yes. So the speed at point 3 is exactly the same as the speed at point 2. So now when I look at this guy, that speed does not change. You have to travel a distance into the rough ice to change your speed. So now, here I go. And here's where we're going to get tricky now. Because look how I drew the length of these guys. These guys are about 2.5 squares. So now, what happens when you get to the rough ice? So now, what we're in here is that we're in this interval of rough ice right here. Right? So this is the rough ice. And what we mean by rough ice is there's friction here. So here we go. How should the next velocity be at point 4? Should it be the same, smaller, or larger?
Smaller because there's more friction, so you're going slower.
Yes, it has to be smaller. So note, if I put it smaller, look that I'm going to be drawing it right onto V1. So look what I do. I'm going to take this piece right here. I'm going to move this down. I'm now drawing my dots down here now. Because if I put it right on top, it gets confusing. But it's still straight line motion. So now when I look at point 4, that velocity has to be smaller. Why does it have to be smaller? Look at the size of the interval. It's smaller. So that velocity then right here has to be smaller. And then what happens? It continues to get smaller. And what we're going to do here is that was 2 squares. You see, I'm running out of space. You know what I should have done? Is I should have done this here. Should have moved. You know what? I need to just move the whole thing down. I didn't have any forethought. Sorry about that. So we'll say that this is the rough ice. And what we're going to do here is that I'm going to reduce this rough ice. And so you could see that if this is 2, I need a smaller interval right there. And I'm going to say that this now is the end of rough ice at this point. So this is the end of rough ice. So this is all the rough ice right there. Okay, so now let me ask you this question. So at point 5, is the speed smaller? Well, we know it has to be smaller because we look at the interval right here, right? We see this interval, and this interval tells me that it's smaller. So we know that the speed here has to now be what? Even smaller. So now what you're seeing here is that now, according to the question, I'm now moving at what? A steady 6 meters per second. So that means in here, what I'm going to have is I'm going to have constant velocity. How fast am I moving at constant velocity? Well, now it's going to be V3, which is then going to be 6. You know what? I made some mistakes here. Look what I should have called that point 4. I should have called it V4. This one should have been V5. So this guy should be V5. At V5, you're going to see here that now I move at constant velocity. So that means that all the dots afterwards here have the same spacing. So now I just continue to move at that same speed at V5. And that's my motion diagram right there.
Can you explain how you are supposed to tell the difference of a change in velocity versus like a change in direction? Because it looks like we're going down. So is that a turn? Like
No, I'm assuming that this is straight line motion.
Yeah, but how, like, if you were given, are you ever like, do you ever have to like look at a motion diagram and tell what's happening? Is that
Yes,
something?
absolutely. It's a picture
So then how would we not know that it's not turning when it's
because
going?
it has to tell you that it's turning.
Okay. Okay.
If it doesn't tell you that it's turning, then you can't do it.
Okay. Thanks.
Okay. So now what I want to do here is that's A. So let me go get B here. So if I go get B, so the same type of thing. So remember, we're not trying to solve this. We're just trying to conceptualize the motion, nothing else. So B says here, the minimum stopping distance for a car traveling at a speed of 30 meters a second is 60 meters. You know what? It might be useful not to put that 60 meters there because I don't want it to get into the way of the thinking here. Including the distance traveled during the car's reaction. So you know what I'm going to do? I'm going to take this 60 meters out right here. Because I don't want people to try to scale things. I want to sort of get you to just look at what is actually happening. Okay. I'm not really liking the wording of this thing. See this, the? I should have said something like, I should have said, what is the minimum stopping distance for a car traveling at a speed of 30 meters a second, including the distance traveled during the driver's reaction time? So how about if we just modify that, because obviously that English is not very good. So so that means here that you're traveling in a car. And when we talk about a reaction time, so if we say a reaction time, that implies that no braking occurs. Only when you hit the brake does the car start to slow down. So that means if you're traveling at 30 meters a second, at some point you see something and then your foot has to go from the accelerator to the brake pedal. So you could imagine then that we go something like this here. I'm traveling some distance per unit time. Let's say that it's right here. And in this situation, what I'm seeing here is that I'm traveling some constant velocity. And let's say that we draw them like this here. And then right here, what you're doing here is that you see an object that you have to avoid. Or let's say that you see, okay, how about if I write that bigger? You see an object in the road. So you do not instantly start braking. Your car is moving during this period. So what that means here is that when I have a reaction time, that means I got to take my foot off the gas onto the brake pedal. So I'm going to travel some distance. So when I look at my speed here, if my speed here at this point in this interval, I am traveling at 30 meters per second here. And of course, this is constant velocity. Now, if I see it here, note that if I look at the size of the interval, that I've been drawing it beforehand, then my speed at this interval here must be what? Must be the same velocity because the interval is the same. So that means as I start to react, it's going to take me a certain amount of time to actually hit the brake. Okay, so here I go. So at this point here, we're going to say that this line here is that you now step on the brake. Question: is the speed at point 4 the same, slower, or faster than at point 3?
Wouldn't it be the same?
It would be the same because look at the interval. The interval between 3 and 4 is the same as the interval between 2 and 3. So the speed is exactly the same length. You do not change speed after you hit the braking, right? So now, again, I'm really not a judge of space here. I'm going to bring this down a little bit here. And I need to really sort of like bring this up and just say, there's my reaction time, which, right? So this is my reaction time right here. And then here I have braking. So this is where braking starts to occur. So when I look at my dots, note that my dots then have to do what? They have to then change spacing. So then I have dot 5. And if I'm going to look at the minimum distance, then I'm going to assume here that the dot then goes to 6. And then at some point, the dot is then going to stop at 7. So when I'm looking at these arrows here, I'm seeing that this next arrow should be smaller, smaller. And then right here, I'm going to say that it stops. So that means V7 is 0 here. So braking then tells me here is that what's happening? I'm changing velocity. And that would be a motion diagram. So note where I'm putting all my time at the intervals. When you go into problem solving, it's the intervals that become the most important. What's happened at these intervals? That's why I'm spending all the time on those intervals. That's the key thing in problem solving.
I have a question.
Sure.
If it stops at V7, would then the distance between point 6 and 7 would there be no distance between those points?
Well, let's look at this here. So do we agree that this interval is different than the previous one?
Mhm.
So then this would be then, let's say this is V5. So then let's look at the previous interval. This interval here is smaller, so I should then have a smaller velocity here. So the question is there an interval between 6 and 7? And the answer is yes. If there is an interval between 6 and 7, then that means that the car must be moving according to my picture at 0.7, which tells me I'm incorrect. So what I'm going to, so we have to sort of like come to some agreement here, which I was being very sloppy here. Because well, wait a minute. Let me see if I could stand corrected here. if I was to draw 7 a little bit better, then I would want a dot essentially like at that point right there. Now, is there a separation between 6 and 7? The answer is yes. But we're assuming that at that point that the separation is so tiny that the speed of the car is probably moving at the growth of a toenail. But there is a tiny one just to essentially indicate the end of motion. Does that answer your question?
Yes.
Okay. Yeah, thank you for helping me out there. I totally blew it on that piece right there.
No problem. Another quick one. Should we then draw another point, like directly below 7 to represent
To
like
represent the
actually
stopping.
0?
To represent the actual 0.
Okay.
So, but there is a slowing down process, and you could see that here it becomes quite difficult to just say, when does it actually really stop? We typically don't care about that, but I think for the intensive purposes, it should be that. It should be exactly like you said. Now, let's go to this next one here. And this is the last one. Okay. So it says a snowboarder glides down a 50-meter long 15-degree hill. She then glides horizontally for 10 meters before reaching a 25-degree upward slope. Assume that the snow is frictionless. So, there was a question earlier about how do we know when there's a change in direction? This is a change in direction. So note that one of these slopes is going to be what? Is going to be 50 meters. So I'm going to try to draw it nice and long. And then there's going to be some horizontal distance. And then there's going to be a very short 10-meter slope. And this slope is steeper. So then I'll try to draw it steeper than with the previous one. So I'm assuming that the length of this guy from here to here is roughly 50 meters, and that the length of this guy here is 10 meters. Okay, so here we go. So it says here, she then glides. So what does it mean when it says glides down? I'm assuming that the speed is 0. So that means I start here, and at point 1, I'm assuming at point 1 that the speed is 0. So now what happens? You start to speed up. So if you start to speed up, what I'm going to do here is that I'm going to draw a dot here, and then I'm going to roughly kind of sketch them in. So then I'm going to just say, maybe it looks like, maybe I should have gone backwards actually. How about something, it's got to be, let me do this again. I'm going to say big space. Yeah, that looks like good. That looks good to me right there. So what you're seeing here is that now I have 2, 3, 4, 5. So now if I come in with my velocities, what I'm seeing here is that there's nothing on 1, but now I'm speeding up as I'm going. And I'm showing my longer vectors here. So now, here's my question. At speed 5, is the arrow bigger at 4 compared to 5? Is 5 going to be bigger, smaller, or the same?
Should be the same.
So let's look at the interval. So if I look at this interval, and then I compare it to this interval, look how the green interval between 4 and 5 is bigger. That means then that the velocity at this point must be longer here. Now, so right as it hits the bottom, you continue to move in that direction. So V5 is then, it's something like this here. Okay, you're going there, and then magic happens. What I mean by magic is V5 instantly changes direction. And as it changes direction, then the speed here at 5 is the same as if it was going straight down. So then I continue here. So then I have 6, and let's say, again, the drawing here is not to scale here. And then I get to 7 here. So then I have a question. At 0.7, is the speed at 0.7 the same, smaller or larger than at 0.6?
It should be the same, right?
It should be the same because it's moving horizontally at frictionless ice. So when I look at that speed, that's, which I should have probably drawn on a different color to separate it out, that speed should be the exact same speed. But then because of the change in angle, it's actually going up the hill at the same speed as before. But then if you're going to go up the hill, you would expect it to slow down. So then here I go. I'm drawing my staggered velocities and dots. And then maybe I'll draw one like this, which is a little bit slower. And I'm going to get rid of this 10 here just to make it a little bit thing. And then at some point, what's it going to do? It's got to stop. So if this would be 8, 9, 10. So at V10, it should be 0. And that's what I mean by a motion diagram here. Okay. I'm then going to move on to the next piece here.
I have a
Oh, sorry.
Go for it.
yeah, I have a question regarding this. So when you first, I'm just wondering how you set up as many dots as you do. Is it just for clarity, or is there...
It's random. It's random.
Okay. Okay. Thank you.
And the reason why it's random is that we're not trying to get the details. We're trying to get the picture. We only want the concept. And the key thing, as I've said several times already, is what is happening at the intervals. That's the most important thing.
Okay.
It sounded like there was another question.
Yeah. So why is there no velocity arrow between 0.6 and 7?
I just didn't draw it in, to be honest. I wasn't trying to be tricky. So it would still be the same.
All right. Thank you.
Okay.